Welcome. It's Friday, but again, we're continuing on with the interesting content. We have another session of open office hours, and we have Ryan back again with us, and he will be talking about different things you can engage with regarding the zkML bounty and trying to provide additional feedback for all of you that have questions for the things that you're trying to build, the questions that you might be encountering already. So anything related to the bootcamp already, we have Zhenfei as well from Polyhedra, who will be facilitating the conversation and trying to preemptively ask questions that might be of importance for yourselves. Please make sure to turn your cameras off. We always love to see some smiley faces on the other side and know the people that are taking part of the bootcamp. If you have any questions, feel free to raise your hand, unmute, ask these questions, or post in chat. Yeah, looking forward to a nice 30 minutes ahead. Over to you, Ryan and Zhenfei.
Hi. Okay. Okay. Is my audio good? Okay. Cool. All right. Thanks for the introduction, and thanks Ryan for coming again to this bootcamp. And I mean the feedback for the last lecture was fabulous, and everybody loves you. I would love to pick your brain on on what we can do, or what we can do for this bootcamp. I guess the top part, the first question. Oh, sorry. Is there anything that you want to share before we jump to the questions?
No, I think let's jump in. Yeah.
Okay, cool. I guess the first question on my list would be like, what do you see as a good application or a good submission, and that has both really good result and also potentially practical applications?
Yeah. So, to me at least, back when, or I guess as we continue to work on zkML things, there are two flavor, or really there's like three flavors of project, I think, which zkML typically really shines in. And I guess when we think about like the kinds of applications, so we'll give some examples in a little bit, but basically we want to think about, well, what are the properties of zkML, or what are the properties specifically that zk gets you so that machine learning algorithms are more secure, more consistent, more like knowable or trustless in some sense. And so the first category or example that I think folks like to use is that of, hey, I have some protocol. All the other parts of this protocol are running on chain. So what that means is that this protocol is trustless in the sense that you can look at the code yourself on chain. Also, only the code which is on chain can be executed, except maybe during this protocol, there is some basically portion of it that requires a machine learning algorithm. So one example of this could be, oh, I have an on-chain like credit score system, except I need some machine learning algorithm to parse all of your previous like financial history or on-chain data or things like that in order to give you a credit score. Now, I think the kind of like easy approach that a lot of folks take is to say, well, everything else is on chain except for the machine learning part. And that part is going to be off chain. And you're just going to have to trust that we're doing exactly what we say that we're doing. However, zkML can really help with this, because what you can do is you can say, no, we're going to still run our machine learning algorithm and we're going to tell you the result. But instead of asking you to trust us, we're going to give you a zero knowledge proof that we actually computed the inference correctly. So this is in the kind of deployment phase where you're done training your model and you've deployed it in the field and it's actually generating some results and you're just proving that it was done correctly. And furthermore, you want to send this proof to chain so that your protocol can consume it and say, I see, this person actually has this credit score or whatever the output of the model is. Therefore, let me continue with whatever the rest of the protocol is. And so this kind of like links basically what the machine learning model is doing to what the rest of the protocol is doing and actually makes that entire loop trustless. So this is kind of the first flavor of, I guess, like application that zkML is really good at. Another flavor of application that zkML is really good at is that of what we're calling like client-side proving, or kind of like local proving. And the idea here is that you have some data that you wish to be kept private, and the service that you're basically interacting with. So in this case, I guess since y'all are the devs, y'all are the service. So for your users, you would like them to keep some data local, but you have some algorithm that you want to run over their data. And in particular, this might be machine learning algorithm that says, oh yeah, let me, for example, do a convnet over your I don't know, ID and pick out just your birth date so that we don't learn anything else about the other things on your ID except for what your birth date is, or even like, for example, if you're over a certain age, for example. So in this case, there's kind of this issue, right? Because you can't have users send you their data because then that breaks the whole privacy thing. But you also don't want to just send your algorithm to the user and just trust that or hope that they run it correctly. Because then anyone can just say, oh yeah, I'm definitely over 21. Let me into this whatever event. And so in this case, you want to not only send them your model, but force the users to give you a zero knowledge proof that they ran your model correctly. And so in this case, the prover actually will go on the user's kind of like client device. And that helps basically secure the algorithm to you as well as preserve privacy for the users. So these are the two kind of primary like inference cases. And then there is a third case, which is that of like training. So in this case, this might be more like researchy, or it might be tougher because training is just much harder than inference. But the TLDR is that you want to show that a model was trained on a correct set of data. Now, what correct means can be kind of up to you, right? But this can mean, oh, the data is unbiased, or it can mean, oh, the data has like good like representation across all these categories, or it can be, oh, the data set isn't like poisoned by these examples that will like cause like trapdoors and things like that in the model. And so in this case, you basically prove that your model trained correctly using, again, a zero knowledge proof over some data set that has been committed to and whose properties have been verified publicly. So there are also other kind of like more out there ideas, but these I would say are the primary like intuitions for like where zkML can be really helpful. Yeah.
Cool. So there's a follow-up questions from the audience. So like how is zkML different from the privacy preserving machine learning?
Yeah, that's a good question. So I think privacy preserving machine learning is not super well defined based on what I've heard. So maybe it might help to talk about the privacy properties that zkML can get you. Yeah, so maybe we'll just start from there. And then maybe some of the properties that it at least cannot get you because zk doesn't get you that. So one privacy property that zkML can get you is the ability to hide the model parameters. And in fact, this turns out to usually be one of the most important features because, you know, you spend all this time and effort training your model. You don't want to just release your model, or maybe you do, right? But let's say in this case that you trained your model on very kind of like expensive, like hard to collect like data sources, and therefore your model weights are usually kind of like really private to you. And so in this case, you can generate a zero knowledge polynomial commitment to the weights that represent your model. And in that case, in the zk proof, you still show that whatever you committed to is the model that's running, even though no one knows what the actual model weights are. Privacy preserving usually refer for differential privacy. I see. Let's see. Last I remember, differential privacy means that it is indistinguishable for a model training on some training set, whether a particular like piece of data was in the training set or something like that. You can also hide the, I guess, like input data. So in the case of the client side proving, you actually would want to hide the input data. So you can get that as well. Like you can hide whatever parts of the model that you would like. But generally, a couple of things that you cannot hide are, one, you can't hide the model architecture. So this is generally the zk circuit and needs to be agreed upon by like the prover and verifier, because otherwise, what are you even proving? And the second thing that can't be hidden is that the prover, whoever it is, needs to know both the model weights and the data at the same time. So unless you're doing some sort of like zk MPC setup, if it's just a pure zk prover, the prover needs to know all the data in order to prove that the circuit was executed correctly. Additionally, let's see, like FHE, etc., can be used in black boxing the computation. I see. Yes. So in FHE, you can basically encrypt your data, send it to a server, and then the server can run their computation over the encrypted data, never learning what it is, nor what the output is, and then basically send you the result also encrypted such that you can decrypt it. what FHE gets you is that the server or whoever is doing the computation doesn't learn what the data is, unlike in a ZK prover, where the prover does need to know all of the data at the same time. Additionally, FHE doesn't get you computational integrity. So just because the server computed whatever operations over your encrypted data doesn't mean that they computed the operations that you expected them to. So ZK, importantly, gets you this extra computational integrity benefit in which you know that the algorithm that the server says it's running with all the parameters that it says it's running is actually the one that's being run.
I guess people are very interested in the definitions of, oops, that's another one. The Expander has OSS toolings for generating sharing commitments to model weights, or other toolings to work with models on ONX and other formats. I guess I can take this one. So yes, precisely the zkPyTorch toolchain that we're developing, we extract the ONX format of the model, and then we compile that into the IR or the circuit that Expander uses. So yes, it does have these tools. Sharing commitments, I don't think we also have the tools to generate commitment, but I'm not sure what does it mean for sharing commitments. Maybe you can, Manish, maybe you can elaborate what that means. While we are waiting for him, let's. I have a follow-up question. So you had 3 applications in mind. One is to by sharing commitments, I mean making a hiding commitment to the model weights. Yes, that's basically you commit to the. That's basically the PCS algorithm in a proof system where you input a model and it generates commitment for you. And there's a follow-up question on the privacy preserving machine learning. So then, is zkML really zero knowledge by definition? Because we never know how the exposure to the data might reveal anything, unlike the FHE where the data is encrypted, as you said.
Right. So zero knowledge in the case of zero knowledge proofs has a very specific kind of formal definition. And the technical way of saying it is that there should, for every zero knowledge proof system, i.e. if you have a prover and a verifier, there should exist another basically polynomial time algorithm called the simulator that without knowing what we call the witness of the thing that you are trying to prove that you know, can generate basically a distribution of transcripts while interacting with the verifier that looks identical to the distribution of transcripts that the prover should be generating. So I guess less formally, what this means is that the verifier in a zero knowledge proof should not learn, quote unquote, anything other than the fact that the prover knows the witness that it's supposed to know. I think in the case of GKR, it's more the statement looks more like, oh, I know basically a set of circuit inputs such that this circuit output is the correct basically application of this circuit structure that both of us know to the circuit inputs, whether they're hidden, such as the model weights, or whether they're input, which is, I guess, sort of like public input that you would put into a machine learning algorithm. So I guess when we talk about zero knowledge, we have to be careful about who is the one that is learning something or not learning something. In this case, the verifier is not learning anything about any of the parts of the circuit or any of the inputs of the circuit except for public inputs to the circuit, which it already knows.
Cool. Let's move on. The next question is also about zkPyTorch. There was some delay on our end on the Polyhedra, and so we will release the zkPyTorch and the tutorial next Monday. Yeah. And there's a follow-up. Public input should be agreed on, right?
Yes. So the assumption is that public inputs are known to both prover and verifier before initiating any of the proving process. Yeah.
Cool. Let's wait for a second to see if there are follow-ups. You're on fire today. All right. Okay. While we're waiting, I'll answer my follow-up question. So on the three applications that you mentioned, do you think which one, like for this bootcamp, which one do you recommend people to build? Like I would imagine like build a training model would build a toolchain for training to prove the training models would be really hard. So do you have any recommendations here?
Yeah, I think definitely to start, I would say, well, to start, I would say forget about the ZK, just make the like AI model work first. So just make it do the thing that you want it to do. And yeah, and all of this is in the first two camps. So either the client-side prover or the kind of like for protocol, like to be verified on chain type thing. But yeah, as in like I would highly recommend probably, unless you want to go down like a much more researchy rabbit hole, which is fine. But otherwise, I would definitely recommend going down the inference route and saying like, yep, we just have a model. We want to do a single forward pass of this model, like whether it's a convet, transformer, or like whatever you want. We just want to prove that basically the forward pass of this model with hidden weights or public weights or hidden inputs or public inputs was actually executed correctly. I also have less experience with the toolchain than I should, so I will also take a look at it. But the toolchain hopefully should make this not too bad in terms of like transforming from like PyTorch into like a GKR circuit, for example. Yeah.
Cool. Thanks. There are two more questions here. First one is on the zkML paper used in Halo 2, based on the KZG and IPA. Is it a potential hackathon idea to use GKR instead of them for polynomial commitment?
Yeah, I'm not 100% sure which paper this is, but is this the MobileNet proving by like Daniel Kang and Stoka Yisun? Okay. Yes. I guess Halo 2 plus, for example, KZG or IPA, that is one entire proof system. So I guess Halo 2 basically says, give me your constraints, and then I will turn it into, or I will reduce it into the correctness of a set of polynomial evaluations for which either IPA or bulletproofs or something like that, or KZG can help you, because that allows you to commit to a polynomial and then generate an evaluation proof for it. In this case, terminology-wise, I would say that GKR is kind of the equivalent to a Halo 2 or to a Spartan or something like that, which basically compiles a circuit and reduces the correctness of basically the execution of the circuit into the correctness of evaluating a couple of, in this case, multilinear polynomials at basically some random challenge points determined by some check. So yes, it is absolutely possible. And in fact, I think Zhenfei / Polyhedra and at least us broadly agree that GKR is much, much better than Halo 2, like substantially better than Halo 2 efficiency-wise, for proving machine learning circuits specifically. So yes, that is exactly the idea. You can also use Halo 2, but it should be much slower, basically. Yeah.
Yeah, we tried. I think Ryan, your team has tried this, and you take like 100 hours.
Yeah.
Or something. Yeah, okay.
It was a little
I
long.
remember that was fun.
Yeah, it was very fun.
But feel free to try, and then you will see why we are pushing so hard for the zkPyTorch.
Yeah.
Let's move on. Another question about Expander. Is it possible to pass in other data to include in a proof of the model's inference as part of the witnesses? For example, could we pass in hash of some data into the prover, a hash that a public value known to the prover and verifier?
Yes, you can absolutely do that. So you will have to do some extra work to almost like concatenate the two GKR circuits, as in you'll have one GKR circuit, which effectively just computes the execution of the model that you care about. And so I just think of each GKR circuit as like proving some property about the data that it's over. So the model GKR circuit proves the property that the output of this model, whatever it is, predicts or generates or whatever this thing over this data. Additionally, if you have previously committed to the data, which I assume is kind of this use case where you say, oh, I'm committing to some data beforehand, and then I'm going to show that for the data I've committed to, it is a blank via a classifier model or something like that. So in that case, you would have another GKR circuit over the same data or the same polynomial that represents that data that basically computes the hash function in circuit. And so you can show that basically the hash in circuit is the same as the hash which you previously both agreed on. And that way you know that that particular piece of data, having been, I guess, like inferenced or whatever, gives you this output that corresponds to that hash. But you just have to basically put the two circuits together, or like to run both circuits and to prove both polynomial evaluations over the same polynomial commitment. So that is important. Yeah.
All right, thanks. The next question would be, what would you like to see built during this hackathon that would have impact in the field?
Oh, interesting. That could have impact in the field. This is a really good question. I think, I know a lot of folks are thinking about machine learning algorithms for DeFi. So for example, I think one of the early thoughts was, if I am supposed to be, for example, a hedge fund or a DeFi hedge fund. Sorry, I also don't know very much about DeFi, but yeah, if I'm supposed to roughly be like a DeFi hedge fund and you send me your, like your currency or whatever, so that I can presumably invest, then maybe you would like to have some transparency into what I'm doing, or whether the thing that I'm doing is similar to what I've been doing before, which is when I got good returns and therefore why you decide to invest in me in the first place. But I don't want to spill my secret sauce, right? Like I don't want to just tell all of my like investors or whatever, like exactly which algorithms I'm running or like the weights specifically for those algorithms. So in that case, you would use a basically zkML type setup to say, yes, I'm using like a similar model, or I've like updated my model in like these ways, such that the back test for these models is still really, really good. And so you can trust that you should still put your money in me roughly. So I think this is one of the use cases folks are thinking about. I think folks are also thinking about like trying to have, I guess, like LLMs, for example, like on chain, and to say, maybe this LLM, for example, is or yeah, maybe there's this on-chain like autonomous world, and you have like this governance structure where some of the folks are like players and some of the folks are like language models. And so maybe you don't want to have zkML for like every single NPC, because that would be a lot of just different I guess like characters. But maybe the president, for example, should be ZK'd, because if someone decides to mess with like the president's like LM algorithm or something like that, that could lead to economic like disaster and other just like terrible things happening in this world. And there's like actually a lot of attention and like money and importance basically on this. So in that case, you would definitely want to kind of LM that thing. I think more broadly for like less specifically crypto focused things, I think folks care a lot about AI safety and robustness right now, as well as in AI research, the ability to replicate things. So one more, I guess, like researchy thing that has always been quite interesting would be to say, I, for example, have this really, really like toxic adversarial kind of like testing set. I don't want to reveal it because I don't want people to fine tune on this data set, but I need your model to basically pass this safety test if we're going to release it into the wild, right? And so it's like, well, you have your model, you don't want to just give it to me, and then I have my data set, and I also don't want to just give this to you. Or rather, let's see, sorry, you have your model, you don't want to reveal it to the public, but you still want to show that basically your model, when executed on my data set, does not give toxic, biased, like terrible responses, right? So in that case, you can privately send me your model. I will run it over my entire data set. I will generate a zero knowledge proof that your model, when run on this data set that has been committed to previously, perhaps with a hash or something, does not produce like toxic or biased or whatever responses, and then publish that result so that everyone can see, oh yeah, this model does really well on this benchmark. These are some vague ideas. Yes.
All right. I guess we have 1 minute. We can take maybe one more question from the audience. Okay, looks like we are good here. Thanks, Ryan, and thanks again for taking time to chat with us.
Yeah, thank you, Ryan. This was great, and I can't say this is going to be the last time we can have you. Like everybody loves having you around, so it's a great pleasure once again. And for everybody else that's here and wondering whether there's going to be a recording, yes, there will be a recording, which we will try to make available to you probably on Monday, and it will be added to the Hacker Pack. Lastly, one thing that people are always asking is there any a channel that Ryan people can reach out to you, whether that's going to be Discord link or Telegram link, something you can share in chat, and we will make sure to share with everybody that's building, and if they have any questions, they'll reach out to you.
Okay, yeah, I'll message you all about that. Yeah, that sounds good. Yep.
All right. Then everybody, once we have that, we will make sure to share. Thank you once again, Ryan. Thank you, Zhenfei, for moderating. Wishing you all a happy Friday and a great weekend ahead. And hopefully see you next week if we're going to be organizing some new office hours. And we'll make sure to announce these in advance so you can all prepare and attend. Thank you all. Have a great day. Cheers.
Thank you. Take care.
Bye-bye.